Good morning, friends. Up to 13.13 numerical of exercise of chapter 13 nuclei we already discussed, right? 13.14 is cancelled for the board exam. Now 13.15 numerical, the Q value of nuclear reaction A plus B convert into C plus D is defined by the equation Q is equal to mass of A plus mass of B minus mass of C minus mass of D into C square. From the given data, determine the Q value and state the reaction are exothermic or endothermic. Here the two following reactions are given. One is 1H1 plus 1H3 convert into 1H2 plus 1H2. And second reaction is given, carbon C612 plus carbon C612 convert into neon 1020 plus 2He4. For this two reaction we have to judge about that this reaction is either the exothermic or endothermic. Clear? Okay. Atomic masses are given to be mass of the 1H2 is 2.01410 atomic mass unit and mass of 1H3 is 3.016049 atomic mass unit. Mass of the carbon C612 12 atomic mass unit and mass of the neon 1020 is 19.992439 atomic mass unit. In this numerical, we have to decide the given reaction are exothermic or endothermic by calculating the value of Q or the Q value of the reaction. If the Q is less than 0, so this reaction is endothermic, and Q is greater than 0, the reaction is exothermic. To calculate the Q, here the general equation of Q value is given mass of A plus mass of B minus mass of C minus mass of D into C square. Right? So we start our calculation of Q value of first reaction. Reaction 1 is, for 1, reaction is given as 1H1 proton plus 1H3 convert into 1H2 plus 1H2 plus Q value. Therefore, Q value of the reaction is into bracket mass of 1H1 plus mass of 1H3 minus mass of 1H2 minus mass of 1H2 into C square. Now we substitute the value. Now we substitute the value of masses of 1H1, 1H2, 1H1 proton. Therefore, the mass is 1.007582 or the 7825. 007825. Plus mass of 1H3 already given 3.016049 minus mass of 1H2 2.014102 minus again the mass of this, therefore 2 times I can add directly minus 2 times the mass of 1H2. Therefore, 2 into bracket 2.014102. That is the atomic mass unit into C square. Now, as we simplify it, so we obtain the Q value is equal to 4.023874. 23874 minus 4.028 4.028 into So 204 u c square. Now we know that c square is equal to u is equal to 931.5 MeV into upon c square. Already we did this relation. One atomic mass unit is equal to 931.5 MeV upon c square. Here we substitute this value. So the subtraction of this portion is minus 0.004 into minus 0.00433 into now value of u 931.5 that much MeV. So the multiplication of this is minus 4.0333 MeV. Thus we obtain the Q value is negative. So therefore Q is negative, therefore less than 0. Therefore the reaction is endothermic. Reaction is endothermic. Again, the equation of the Q is given Ma plus Nb, that means the addition of the mass of this A and B, minus subtract the addition of the mass of C and D into C square. So this way we can find out the Q value for the given reaction. For first reaction is 1H1 plus 1H3, convert into the 1H2 plus 1H2 plus Q value. Therefore the Q value of this equation is mass of 1H1 plus mass of 1H3 minus mass of 1H1, 1H2 minus mass of 1H2 into C square. Here we substitute the value, mass of the proton 1.007825 plus mass of 1H3 already given 3.016049. Here 2 times the mass of the 1H2, therefore 2 into 2 point mass of 1H2 2.014102. That is in atomic mass unit into C square. Right? So as we simplify it, therefore Q is equal to 4.033. Right? 4.023874 minus 4.028204 atomic mass unit into C square. But we know that atomic mass unit is equal to 931.5 MeV upon C square. MeV upon C square. Substitute here the value. The subtraction of this bracket is 0.00433 into 931.5. That is the value of U. And unit of U is MeV upon C square into C square, C square, C square cancel. Therefore, we obtain the unit is only MeV. Then thus we obtain the Q is equal to minus 4.0333 MeV. So here the value of the Q is negative, therefore reaction is endothermic. Now the second reaction is carbon C612 react with the carbon C612, convert into the neon 1020 plus 2He4 helium and the Q value. Find out the Q value. Therefore Q is equal to 2 times the mass of carbon C612 minus mass of the neon 1020 minus mass of helium 2He4 into C square. Substitute the value twice of mass of the carbon, already given this 12.00 atomic mass unit minus mass of neon. Mass of the neon is 19.99 2439 minus the mass of the helium. Now the mass of the helium 2He4. Therefore the 1H2 twice time the mass of the 1H2. Therefore minus 2. 1H2 as the mass is this 2.014102 into C square. H is simplified, so direct I write down the answer of this is 0.02888 into atomic mass unit into C square. But U is equal to 931.5 MeV upon C square. Therefore 0.02888 into 931.5 MeV. Right? So is equal to, just a minute here, 24, right? So its simplification is what this 0.04 49588. So the simplification is 4.618377 MeV. Right? Therefore, Q value is 4.618 MeV. That is greater than 0. Therefore, the reaction is exothermic. Reaction is exothermic. Clear? Here the numerical value we have to substitute and calculation is required to find out the Q value, and if the Q is less than 0, reaction is endothermic, and if the Q is greater than 0, the reaction is exothermic. For this, here the Q value is positive, while here the Q is negative. Clear? Okay. After that, the next numerical is also similar. Suppose we think the fission of the Fe2656, that means the iron, into two equal fragments of aluminum 1328. Is the fission energetically possible? I give the working out Q of the process. Again, as we think the fission of iron into two equal fragments of aluminum, is the fission energetically possible? I give the working out Q of the process. The mass of the Fe iron is given 55.93494 atomic mass unit, and mass of the aluminum is given as 27.98191 atomic mass unit. Now first the fission of Fe2656 into two equal fragments of aluminum 1328. So the reaction is Fe. Here 2656 convert into aluminum 1328 plus aluminum 1328 plus Q value. So this fission is energetically possible or not? For reaction becomes the energetically possible. For that purpose the Q must be less, that means the Q must be greater than 0. If you obtain the Q value of this reaction is greater than 0, that means the positive. So this fission is energetically possible. If the Q value is negative, That means the endothermic process is required, and for this process we had to apply the energy externally. Therefore, the reaction is not possible energetically. Clear? Therefore, we had to acquire, or we had to calculate the Q value. Therefore, Q value of this reaction is mass of Fe 2656 minus twice of mass of aluminum 1328 into C square. We substitute the value. Mass of the Fe is given 55.93494 minus twice of mass of aluminum 27.98191. That much atomic mass unit into C square. So 55.93494 minus 55.96382 into atomic mass unit into C square. But we know that atomic mass unit is equal to 931.5 MeV upon C square. And the subtraction of this bracket is minus 0.02888 into 931.5, that much MeV. Now this subtraction is negative, that means the Q value is negative. Therefore, Q value is equal to minus 26.90172 MeV. Thus, Q is less than 0. Such fission of Fe is not energetically possible. Because here the Q is obtained is negative. Therefore, the endothermic process takes place, and for endothermic process, the energy is not released. Therefore, this fission process is not possible energetically. Clear? Actually, in these two numerical 13.15 and 13.16, there is depends on the Q value of the reaction. How we have to find out the Q value? Like this manner. Clear? Now the next numerical is 13.17. The fission properties of plutonium 94 to 39 are very similar to those of uranium 92 to 35. The average energy released per fission is 180 MeV. How much energy in MeV is released if all the atoms of 1 kg pure plutonium undergoes the fission? Right? That means we have to find out how much energy is released due to the fission of 1 kilogram of pure plutonium. Okay. So first we have to find out the number of atoms in 1 kilogram of plutonium. Due to the fission of 1 plutonium atom, 180 MeV energy is released. Right? So after finding the number of atoms in 1 kilogram pure plutonium, we have to multiply this number of atoms in 1 kilogram plutonium with 180 MeV. Right? So that much energy is released. Very easy numerical. So first, the number of atoms. Here the atomic mass of plutonium. Atomic mass of plutonium is 239 gram. Therefore, in 239 gram of plutonium, the numbers of atoms is equal to, evoke into a number, Avogadro number is 6.023 into 10 is to 23. Okay. Therefore, in here 1 kg, that means the 1000 gram of plutonium, the numbers of atoms is equal to n, we have to find out. Therefore, n is equal to 1000 into Na upon 239. We substitute the value of Avogadro number 1000 into 6.023 into 10 is to 23. That is the value of Avogadro number divided by 239 gram. Okay. Therefore, the simplification of this is 0.0252 into 10 is to 26. That means 2.52 into 10 is to 24 atoms per kg of plutonium. That is the value of number of atoms in 1 kilogram pure plutonium. Right? Okay. Due to the each fission of atom, due to the fission of each atom, 180 MeV energy is released. Right? Therefore, due to the n fission of atoms, the fission of n atoms, how much energy is released? From the energy is from every atom of plutonium is equal to 180 MeV. Therefore, total energy released E is equal to 180 MeV into N. 180 MeV into N. Now, 180 number of atoms 2.52 into 10 is to 24. That much MeV. So it's equal to 4.53 into 10 is to 26 MeV. Energy is released due to the fission of 1 kilogram pure plutonium. Okay, where is in numerical? First we need to find out how many numbers of atoms in 1 kilogram pure plutonium. We find out this. Now, here due to the fission of every atom of plutonium, 180 MeV energy is released. So due to the n fission of n atom of plutonium, how much energy is released? That much. 4.53 into 10 is to 26 MeV. Clear? Okay. Where is he? And also there is the important numerical for 3 marks. After that, the next is quite lengthy numerical. 1000 megawatt fission reactor consumed the half of its fuel in 5 years. Right? How much uranium-92-235 did it contain initially? One nuclear reactor is given, and the power is 1000 megawatt. Right? The half of initial fuel is consumed in 5 years. So we have to find out how much quantity of uranium initial. Okay. Now assume that the reactor operates the 80% of the time, that all the energy generated arises from the fission of uranium-92-235, and that this nuclei is consumed only by the fission process. Okay. For that purpose, first the Avogadro number Na is equal to, here we consider only 6 into 10 is to 23 atoms per mole. Right. Now, power of reactor is given 1000 megawatt. power of reactor, there is a capital P, is 1000 megawatt. That means the 10 is to 9 watt. 10 is to 9. Okay. Now time is given to consume the half fuel. Time T is given the 5 year. Convert into second. Therefore 5 into 3.154 into 10 is to 7 second. Therefore 1.577 into 10 is to 8 second. That is the total time. Okay. So in that much 5 year time, that means 1.577 into 10 is to 8 second time interval, the half of the fuel is consumed. Okay. Now the reactor is on only for 80% of that time. Therefore, time for reactor to continue. Time for reactor to continue is, there is capital T time is equal to 80% of small t time. That means the 0.8 into 1.577 into 10 is to 8 is equal to 1.2616 into 10 is to 8 second. For this time, the reactor is on, but the reactor is continuous. Yeah? Okay. Now, power consumed in this time, how much power is consumed? In time, capital T is P dash into T into P. This P is the power consumed per second and total time is that much second. Therefore, 1.2616 into 10 is to 8 into 10 is to 9. That means 1.2616 into 10 is to 17 watt. That much power is consumed during the reactor is on. Reactor is on. Clear this thing? Again, the given data is evaporator number 6 into 10 is to 23 atoms per mole of the atom per gram. Power of the reactor P is equal to 1000 megawatt. That means the 10 is to 9 watt. Right? Okay. Now the time to consume the half of the initial fuel is 5 years. So convert this 5 years into second. So we obtain the 1.577 into 10 is to 8 second. Now time for reactor to continue. Here the reactor is only 80% of the time is continuous, while the 20% time is switch off. Therefore, how much time the reactor is continuous? Therefore, T is equal to 80% of small t. Therefore, 1.2616 into 10 is to 8 second. Okay. During the reactor is continued, that means the on. How much power is consumed? So PDS is equal to T into P. Therefore, 1.2616 into 10 is to 7 watt is consumed power during the reactor is switched on. Now, how much energy is released? Now the energy released is 200 MeV. 200 MeV. Now, energy released in every fission is equal to 200 MeV. Right? Convert into the joule. Therefore, 200 mega, that means the 10 is to 6 electron volt. Convert this electron volt into joule. Therefore, we have to multiply 1.6 into 10 is to minus 19 joule. Thus, we obtain 3.2 into 10 is to minus 11 joule. So that much energy is released due to the every fission of single atom of uranium. Now we have to find out, our aim is to find out the initial quantity of uranium. Initial quantity of uranium. Here that much energy is consumed per second. To produce that much energy, how much number of atoms is required of uranium, and from this number of atoms we can find out the total amount of, or the initial amount of uranium. Okay. Due to the one fission of uranium, that much energy is released. Therefore, the number of uranium in 235 gram is this, and therefore the number of atoms in 1 gram, numbers of nucleus or atoms in 235 gram of uranium is equal to in. Therefore, the numbers of atoms in 1 gram of uranium N is equal to 1. Therefore, number of atoms in 1 gram of uranium N is equal to in A upon 235. N 6 into 10 is 223 upon 235. Thus you obtain 2.553 into 10 is to 21 atoms per gram. Okay. How much energy it is from 1 gram? Therefore, energy released from 1 gram uranium is EDS is equal to E into N. E already we found. How much energy is released? 3.2 into 10 is 2 minus 11. So 3.2 into 10 is 2 minus 11 into N, 2.553 into 10 is to 21. Therefore, 8.1696 into 10 is to 10 joule energy is released. So due to the 1 gram of uranium, that much energy is released. Now, the energy consumed by the reactor is this 1.2616 into 10 is to 17 watt. That means the joule per second. Right? As we take the ratio of the energy consumed to the energy released by the 1 gram of uranium, we can find out the quantity of uranium. Right? Therefore, the amount of uranium consumed in 5 years is equal to total energy consumed upon energy of 1 gram, or the energy obtained from 1 gram. From 1 gram. Therefore, 1.2616 into 10 is to 17 divided by energy from 1 gram, 8.1696 into 10 is to 10. So it gives the 1.544 into 10 is to 6 gram. It means the 1.544 kilogram. So that is the mass or the quantity of the uranium consumed in 5 years. But initially here given the half of the fuel is consumed in 5 years. Therefore, the initial amount of uranium is double of this. Now listen, only half of fuel is consumed. Therefore, initial amount of uranium is double of this 1544 kg. That means the 3088 kg. Clear this thing? So actually quite lengthy numerical. So keep in mind that how we calculate it. So read carefully, the data is given. The time for the reactor continuous is 80% of time T, right? The 5-year time interval is given. Corresponding to the 5 year, we have to convert into the second. Therefore, that is the time for which the reactor is on. Okay. How much energy is consumed in T time? So T is multiplied with the power. Power is already given. So we can find out during the reactor is on how much energy is consumed. After that, due to the evaporation of the uranium nuclei, 200 MeV energy is generated. So convert into the joule. Now, first we have to find out what is the number of atoms in 1 gram of uranium. And due to this number of atoms, how much energy is released. Therefore, in 235 gram of uranium, number of atoms is equal to Na. And the number of atoms in 1 gram uranium is 2.553 into 10⁻21 atoms. Energy released from 1 gram of uranium is number of atoms in 1 gram into the energy released due to the 1 nuclei or the 1 atom. So that much energy is released due to the 1 gram uranium. Okay. Total energy consumed when the reactor is on is 1.2616 into 10⁻70 divided by the number of energy obtained for the amount of energy obtained from the 1 gram. So we can find out the quantity of uranium that is consumed in 5 years. Okay, but initially there is given in 5 years the half of the fuel of uranium is consumed. Therefore, the initial amount of the uranium is double of this quantity. That means the 3088 kilogram.